Hi all, welcome to today's class. So let's have some generic discussion on the project that you started working on. Any questions on that? Do you want to do a roundabout? I got some emails, say from Manish, etc. Manish mentioned, for example, that let's see, that we have a couple of questions that we can address in the class if you have time. So we can spend a little time on this. Looks like you did some random forest practice and started sharing some Git link for the project as well. I'm not gone through it. I just got your email, but just looking at it, looks like you're working with the diabetes data set, right? The PIMA, I guess.
Yeah. So the question was, I myself introduced few NAs in that. Like I did not have any missing values, so I used the CSV and I myself introduced few NAs in that. And do you think going that way is good or?
I mean, it's okay for learning purposes. You can do that. Yeah. I mean, in real life, when you don't have missing value, you obviously won't create missing value because well and good not to have missing value. But yeah, for learning purposes, you can do that. But the question is, what percentage of NAs have you introduced, right? So, what is the dimensional data set? Oh, you introduced what?
It has like 737 rows. So in that, it has 13 columns. So in that, I introduced 37 NAs. It's very low, but I was thinking to put in more. And I had one more question, Pranit, like regarding the plotting. So you wanted us to plot against, if this is a regression problem, so you wanted us to plot against a resultant, all the values of the rows, right? So is it against each input versus the resultant value, or I mean, how do we go with that?
Yeah, so each input variable, which we call feature, right? Each feature versus the resulting variable is called the response, not the value.
Yeah.
So one variable against another variable.
Oh, can you repeat that, please?
So it's a XY plot, right? Like a scatter plot. So you're just plotting one axis where will be one of your input feature variable.
Yeah.
The response variable, the variable you're trying to predict.
So say if I have 13 inputs, 13 futures, and one label. So each future versus a label, each future like that, or 13 futures combined versus a label.
Okay, there's some new information coming in. So label, if it is there, it should be a classification problem. Label is not a regression problem.
Oh, sure.
Right. So regression is predicting a real valued number.
Yeah.
Something like stock price or some house value. It's a real number.
Yeah, this is a.
If you have labels, it's classification. So yeah, you cannot plot label because label is not a number. It is just a it's like a bucket, right?
Yeah.
You cannot plot the word spam and no spam. It's not on the number line.
Okay. Sure. Yeah, got it. Yeah, I know I got what you're saying.
Sure. Yeah, but you can do box plots of individual variables if you want.
Oh yeah, I did that. Yeah.
The input variables. And then, good.
Pranit, I had the same too. So if we have like mentioned, if we have 13 features, then it would be like 13 different box plots.
Yes, that's true. You don't have to do it usually for every time. I mean, if you have too many features, you can skip that process. You can only box plot them based on any requirement if you have under some investigation if you're doing. Yeah, if you have,
I have just 9.
You don't need to do 1,000. Hello. Yeah. Any other questions? Yeah, it seems like I'm not able to hear Manish. Okay, I think let's keep going. Any other questions?
Yeah, Pranit, this is Manideep.
Sure.
I tried to work on the dataset on Thursday, but I felt some difficult understanding it. And I have a lot of folders in there. And he gave me so many training sets. I don't know what is that. So I dropped you a mail on that.
Okay, let's.
So anyways, I have a time this week. I'll work on it soon if you.
Okay, yeah. It says I want to select a different data set. Can you please size one? June, can you? Okay, the one you currently were looking at is the Facebook comment volume data set, right?
Yeah. Yes.
So what kind of confusion was there? Let's see. Okay, you put screenshots, well and good. So I don't need to open it again.
Yeah.
So basically, you have a lot of files saying features, right?
Yeah.
Let me share screen. Okay, so you send this email. So when you download it, you got testing and training and some file like this, some PDF. And then this is within training. You have a lot of files, okay. And then you have a test set.
Yeah. And each training CSV has same number of rows, like 40,000 or something.
Okay. There is no other README file or anything on the website, etc. On why?
Hey guys, I lost connection. Can you guys hear me now?
Sorry?
I lost the connection actually just now, so I'm back. Can you guys hear me now? Like,
Yes.
Yes, I can. This is okay. Yeah, we can hear you, Mani.
yeah. Thanks.
Yeah. So we thought, yeah, if you have other questions, we can again catch back after Manideep and Kamal.
Sure. Thank you.
Okay, yeah, cool. So let us see. The dataset contains 5. Yeah, he wrote it here. The dataset is uploaded in zip format. The dataset contains 5 variants of the dataset. For the details of the variants and detailed analysis, read inside the research paper. So you can possibly use any of the variant as long as so the test set has multiple files in it, because I don't see what's inside it.
Yeah, it has the same
And numbering, right? So if you choose, say, we can choose anything. If you choose feature variant 1 in training, do use the same variant 1 related test set.
okay. Yeah, it has actually 10 different CSVs and 10 different ARFFs.
Yeah, ARFF is just a different file name, I guess, right? Just different format. You can
I see 20 files in test set. That's it.
Yeah, and then training has only 5 or even more than that?
Training has 5 variants, like 5 CSVs and 5 ARFs.
And test has 20.
Yeah.
Okay, then we need to be careful. Yeah, we need to go through this paper and see, because if you train on a data set, you should test on a corresponding data set, right? As long as the variable names are same, then you're okay. If variable names are as well different, then you cannot test your model, because you trained on 5 kind of variables. In test set, you have some other variables data. That is not the right way to do. So yeah, I will open the zip file and see myself as well.
Yeah.
And go through this paper a little bit. If not, we can also select another data set, obviously. Either way is fine, because you've not started in it yet. So
yes, yeah.
Okay. Maybe you can search other data sets and email me as well. It's something that catches your eye, like we did originally with everyone.
Okay.
For your initial set that you selected, we can select another one if you wish.
Sure.
Cool.
Thanks for it.
Yeah. Cool. Yeah. Kamal and Thiru, any questions? Yeah, Thiru, go ahead.
Brian, do you want to... Brian, can you hear me?
Yes.
Yeah. Do you want us to actually import some of the missing values and try upon all the pre-processing and missing data techniques? Because I don't have any missing data in my data set, but looks like there are a couple of methods we don't know how to do and all that stuff. So do you think we should find another data set which actually has missing values and do all these techniques?
I would say, learning the imputation, doing that is always a good idea. That I will agree. So if your data set doesn't have missing value, instead of finding another one, you can actually just sample some random values, random locations, and make them missing in purpose. That will be a better way. And it's also a good way, because now you know what values were originally there in that before you made it missing.
Yeah.
Right? Before another in your pre-processing and imputation technique, you can also see how close you got it got to the true values in terms of estimating the missing value. So
yeah, because if we want to see about the class imbalance and all that stuff, we need some missing values in there, right, to see how good the columns are dependent on the response variable and all that stuff. So
these are two different things. Class imbalance is different, nothing to do with missing actually. But missing values, yeah, so there are two different things. Let's tackle them separately. So class imbalance is only if you have like one class being labeled as a more majority class and less other class has like small number of samples, right? So if you had spam, no spam, or simple cartoon data set, if you had 99% of your rows are no spam and 1% is spam, labeled as spam, then it is a imbalanced problem. It has nothing to do with missing values. Missing values can be there or cannot be there, need not be there. It's not a necessity there. As long as the counts of your classes are different, it's an imbalance problem. So that you can always deal with. I'm not sure in your initial data exploration if you already counted.
So when you said counting the number of records in a class, did you mean counting the column length for each attribute, or what? Because it looks like we would ultimately get the same count for all the columns.
So you have a class. Okay, yeah, I'll ask you a couple of questions. Let's dig through this. So do you have a classification problem?
No, mine is a regression problem.
Okay, so if you have a regression problem, you won't have a class imbalance issue at all. Like that doesn't come up. It doesn't come up in a regression problem. So yeah, that is a problem that only comes up in classification.
Counting my columns and realized everything is same. Then I went and looked into class imbalance and stuff. Then I realized class imbalance would be for a classification problem.
Right.
But yeah, but then you want I in the last class you wanted us to see about the columns and stuff. So I wanted to ask you, and I talked to Manish. He said maybe missing, if we have some missing values in some of the columns, so we might end up getting a different count for each column, right?
Okay, I think, yeah, I hear your question, but there is some confusion I'm able to see. So the missing values is for input features, input variables.
Okay.
Your output variable is going to be complete. It's not going to have missing values. That is a missing value problem. Okay. So when you do the class imbalance, if your output variable was a label variable, say in a classification setting, the class imbalance is only counting how many class do you have only within your class variable.
Right.
Okay. So there is nothing to do with missing values there. Now you don't have to count on the input variables at all. I agree. If you count, you will get different counts, but you don't have to count. That doesn't have anything to do with class imbalance.
Right. I think I got it, Pranit, now.
Yeah. Yeah. Cool.
We start class imbalance differently.
Yeah. So nothing to do with input variables for class imbalance. So these are two different issues, but practically speaking, because you're working on the project for next steps, one thing you can do if you're sticking to a current data set, you can always generate some missing values, randomly sample. Don't put missing values in some pattern, just randomly sample. You can use the sample function. It will tell where to put missing values. Those things you note down. You don't need to note down. You have the original data set anyway in a copy. So you just make those values missing and then you apply your imputation in all the pre-processing routine. You can also compare with original entries. If you're in regression, don't worry about class imbalance. We will do another project as well. So the ones who did regression now will do classification in another project. The ones who did classification will do regression in that second project. So that should be okay. And the ones who are already doing classification now, if you have a class imbalance issue, then you have to deal with the whatever I wrote in the document, which we will keep updating every time. So any other questions? Kamal and also Manish, I know you came in the middle.
Yeah, I got some clarification.
Yeah.
Okay. Yeah, go ahead, Kamal.
Sorry. Like I have only like 2.5% missing values. It's
Okay.
like 16 out of 699 rows.
So not rows. So basically, how many columns do you have? 699
I
rows.
have like the like 6. Sorry.
It got choppy actually. Sorry, I was not able to listen. You said 699 rows and about how many columns? Okay, so and then how many numbers were missing? You said
16 numbers.
16. Okay, so basically you have 699 times 10, right? So you have 6,990 entries.
Yeah, one of the column is like a code of the, so probably it's like 9.
I'm not sure I completely understood what you said though.
First column is like a sample code number. And really specify anything for it doesn't contribute for the classification, I guess.
Okay, so in that case, what we can do is 699 times 9 instead of 10, right? Because then we have 699 times 9 is equal to, let's see, 6291 entries. And what you have is 16 missing, right, out of 6291. So it's basically, it's not 2.5%, it is 0.25% because 0.0025 is missing. So it's like almost nothing is missing, right? You know, it's like very small percentage is missing. Yeah.
Yes.
So yeah, you basically count the number of entries, and based on that, you will say what percentage. Instead of based on number of rows, then you will get 100%. So, but nevertheless, you have to deal with the missing value, right? So you can apply the imputation algorithm.
Of course, yeah.
Yeah. Cool.
Yeah. Okay. So I'm stuck at the box plots. So maybe after this class, I will work on it a little bit more and I will submit.
Sure, definitely. And are you doing classification or regression for the first project?
Classification.
Okay, yeah. So yeah, you might want to also check for class imbalance and everything and see how the balance is. If not, you want to apply some technique, you can ask me. I will see where we are on the drive in our common document. I can keep updating that document where you'll have next steps include as you keep going. Okay, any more questions?
Hey Pranit, I have one last question.
Yeah, go ahead.
So in this Prima Indian data set, like it's a classification problem though, but in the, when we predict something, what do you call it? So in the last column, when you're predicting something, it's giving 0 or 1. So if 1 is for, if she has something, and 0 if they are not diagnosed with diabetes. So So what they did is they already, I think, applied one-hot encoding and they converted that to 0 and 1. So what I was thinking was I'll replace this 0 and 1 with actual some value and then do this encoding to, you think it might help me in practicing those, right?
Well, the one-hot encoding needs to only be applied on input variables, your feature variables that are categorical.
Okay.
Yeah,
okay, got you.
Output variable, you don't have to do one-hot encoding.
Yeah, got it. Sorry.
Right.
Yeah.
Okay, cool. Any more questions, concerns? Okay, yeah, looks like, I think we're halfway mark. So yeah, let's spend the rest of the time discussing our class. So our next topic is going to be something that is very popular these days for the right and as well as a lot of wrong reasons. Nevertheless, it is a reasonable technique. So we're going to be going over neural networks, which is also some sort of a foundation for you when you start learning about deep learning in the future.
Pranit, quick thing.
Yes.
Can you explain us about the out-of-bag error for the random forest?
Tell you like explain more about it, like what it means, or like if you can add in some more the part that is
like what it means, and is it like same like how we have to calculate out-of-bag error?
I see. Okay. And also there are different ways you can come across this. Did you come across out-of-bag error when you applied the random forest in terms of the summary that R returns? Because R returns a specific format of output, right? Is it there or?
I was just random forest and explained it a little bit, but I couldn't follow what he was telling me.
Oh, okay. Okay, sure. Yeah, I was trying to get some context, right, so that I can tell you about it. Otherwise, I can tell you something about out-of-bag error that won't be relevant to what you were thinking about it, right? What was confusing you? Okay, cool. Well, so let me do some quick, just some drawing. You can see my screen, right? Yeah. Okay, so that's your data set. This is your label column. And then you have a lot of input columns here. I'm not drawing all the lines. This is your input variables. These are your rows, different samples, right? So what random forest does is you can do, so out-of-bag error is like cross-validation error. So basically it basically resamples. And what does resample refer to? It basically is sampling, but with replacement. It's called resampling. It's just a terminology. So when you take a sample out and if you put it back before taking the second sample randomly, then it is with replacement, which is called resampling. So basically you resample some rows out. So these are all your rows in your data set. So when you, maybe in your first resample, if you totally had like 1,000 rows in the first resample, if you took maybe 30 rows, so maybe this row got selected, this row, then maybe this row, and some other rows got selected, some other things didn't get selected, right? So it's basically you're training on those rows, you're generating your tree and everything. Your model is being generated, and now when you predict on the rows that were not used, so it's basically a test error. That is known as the out-of-bag error in this context. So you're basically, it's something like cross-validation error. You're basically doing the training error, test error kind of thing. So you want to see how you're performing in the sample that you didn't pick. So now what will happen is you'll generate one resample. You got one out-of-bag error on the rows that were not used. So the ones I put dashes inside were used in the model, the rest were not used, right? So on the not used rows, you will generate your prediction. The truth is, when you generate predictions, you only pass the input variables. But when you train the model, you pass both input and output. So now when you pass only input variables, when you generate predictions, you can compare them with the true output that you know, that the model doesn't know. So you try to predict these numbers. So you compare with that. Now that is one number, so E1. And then what you do is you generate another resample. The second time maybe some other variables got selected for training and the rest will be test. So on the test you get another sample. You can average those errors. It's called the out-of-bag error. Another terminology is called out-of-sample error as well. So you're basically, in-sample is what you're using for training the model. Out-of-sample is where you're predicting basically. Any other question? Some more extensions or anything?
No, I'm good, Trini. Thanks. Thank you.
Cool. Yeah, so let's get started on the neural networks. So yeah, like I was saying, some quick background. This is the foundation for learning deep learning, because deep learning is nothing but some modified architecture of standard neural networks, right? There are different kinds of architectures and different kinds of deep learning techniques, but everything, the basis is about neural networks in general. So this slide is something that I have not created as part of NumberDocs. This is a very popular slide from Andrew Ng, Stanford. I think these slides or some version of it, he would also use it on Coursera, I guess. And as you see, it's being used by some other professor in UPenn, University of Pennsylvania, as part of some particular lecture. So this is something that is open source, and I thought let's use this itself because it's very popular in general for this particular lecture. So I will not go through every single slide. I will go through the ones that are most important that we need to focus on. So he's put in a lot of background from a biological perspective on why it is called neural networks, but it's more of a marketing thing as well, although there is some philosophical connections to how neural networks really function in a human brain or in a brain in general, of a living being. But we don't want to really go through that, because in all honesty, the way the neural network works has nothing to do with biology. It is just fascinating that it has some good parallels to what we think about neural networks in a human brain. It has good parallels, so that I will completely agree. But what most people would disagree is that this is how a human brain works. It's not how a human brain works. A human brain is way, way, way more complicated than how a neural network works. So basically, a neural network, I think you can say it is inspired by the functioning of a neuron or of a brain. It's just inspired by it, but it's much, much simpler than a human brain. So we don't want to study about the human brain as part of this course, given these very weak connections. So that is the reason I'm skipping all of this, right? There's nothing to do with the math in neural networks versus this. It's just fascinating that the technique was inspired from a biological perspective, which is good. So we're going to skip this. This is not a neurobiology class or anything. So we're going to skip all of that. Okay, yeah. So neural networks, origin. They're algorithms that try to mimic the brain, right? Which is what we're trying to say. There was a period initially when neural networks were very successful with handwriting recognition and problems like that back in the 80s and early 90s. And then a lot of other techniques like support vector machines and random forest, everything came up, and they were outperforming neural networks, the neural network architectures that existed back then. And recently, with the deep learning, boom, they got really popular again. So it's kind of a resurgence now in more recent times, for the last few years. So yeah, this is where the true stuff starts as far as the formal working of a neural network. So nothing to do with the brain here. So basically, this is an architecture for a feed-forward neural network technique. That's what he wrote here. So this is how it works. Your data set goes into what is known as an input unit. We're going to define this very clearly. There is some processing that happens to your variables. And then another set of units, another set of outputs are created, and they call them the hidden units. Then again, another processing gets created, and then you get the output units. This is like your random forest leaf. This is the output unit is where you have the results of what the regression prediction is, or of what the label is that is being classified, etc. Now, this is known as a layer. Like each thing is an input layer, there's a hidden layer, there's an output layer. This is standard terminology. The thing is, you always have one input layer and one output layer, but you can have many, many layers of hidden units. So you can have one layer of hidden going into another layer of hidden. You can have as many as you wish. But if you have way more than required, then you're going to be overfitting, right? Then your cross-validation error would be low. Although your train will be bad, it not be good. So you want to figure out how many, and then these nodes are called neurons as far as terminology goes. So you want to figure out, in terms of cross-validation, right? In SVM, you work with cost and gamma. In random forest, you're working with number of trees and a variable called mtry, which you're trying to cross-validate on. And the parameters to cross-validate on for neural networks, this is important to know, because for practical purposes, you need to cross-validate. You need to know what parameter you're cross-validating for. So the ones you need to tune are basically only two in a feed-forward neural network. One is the number of neurons per every layer. So you can have 4 neurons here, but in every hidden layer, you can have, say, 100 neurons in one hidden layer and 300 neurons in another hidden layer. And then another thing you want to cross-validate on, apart from number of neurons, is the number of layers. Do you want to have 2 layers, 3 layers, 1 layer, maybe a million layers, right? Depending on the problem. If you choose too many neurons and too many layers for a problem that it does not require so many neurons and so many layers, then you will be overfitting, because your training error will be low, but when you use it in prediction, it will be performing very bad predictions, right? It won't be predicting anything correctly or classifying properly. So, and same way, underfitting is if you require some amount of neurons and hidden layers to perform well in terms of prediction and test data, but if you end up training a model using much fewer neurons or much fewer hidden layers, then basically you have a complex prediction problem, but your model is way too simple. So then even then your error will be bad. You're not predicting properly. So moving on. What is in a simple layer? I think I need to. Okay, I have a phone ringing. I think I will be back in a second. Sorry. Yeah, sorry about that interruption. So we're back. So here I'm expanding upon what is the math that is happening inside each neuron and inside each layer. So basically, if this was your first layer, all that is happening is here for notation purposes, X is your data that is going into the layer. So each thing is going in. You're basically learning a weight vector. Here the weights are denoted by thetas. So that you can think of the operation that happens from neurons towards the weights as follows. All you're doing is a linear combination. Means what? You're doing a weighted sum basically. So it's a sum of products. Another way, so all three are same thing, sum of products, which means theta naught times x naught plus theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3. So the products get summed. That is the operation that happens in here. And then before the output layer, another operation gets happened, which is you pass the sum of products into what is known as an activation function. The sigma is saying the sum of products are being done. And then you pass it into, this is showing an activation function. You basically pass it into another function. Here they're using G for that, for example. So the activation function, that is there are different kinds of activation functions that you can do. A popular activation function is known as the sigmoid activation function. So basically this is how the function is defined. So basically in Z, since you're passing the activation function, the sum of products into the activation function. So basically G of theta transpose X is equal to this thing, because in terms of Z you put in the theta transpose X. So this is an operation that is happening from one layer to another layer. So going back, going forward, right? This is your data. It is going into the hidden layer. This is your input layer, input data, which is your axis. In the hidden layer, basically every line here has some weight with which you're multiplying your input. And then once you go here, you're basically summing up those weights. And then you can do that again. If you had another layer, you're again multiplying, doing the sum of products or whatever is there in the result of this layer, you're doing sum of products again. You can keep on doing the sum of products, but the weights in here are different from the weights here because you don't have to weight them equally. The weights are something that you're learning as part of learning the neural network. The parameters are basically number of layers and number of neurons per layer, per hidden layer. So number of hidden layers and number of neurons per hidden layer is what you tune for. But what is the model fitting? What is it learning? The unknown parameters are basically these weights at each of these lines. So if the weights are tuned properly, then all this operation goes in, and you can do this as many hidden layers as you want. In this picture, there is only one hidden layer, which is this. And then the final, just before the output layer, because these weights are not your regression or classification, it's not a label, right? Just a bunch of weights and a big operation of what to sum and what to product and how to add these things up. All that gets done. In the end, it goes through the activation function. The activation function either returns a regression solution or a class label, basically. So it has those properties. Because the sigmoid activation function, for example, that we are using, has this kind of a shape. So most rows would either be close to 0 or close to be 1. Will be close to 1 because very quickly it jumps to 1 basically. So if I draw it even clearly, it looks like this. So this was the axis. Your sigmoid activation function looks something like this. This one, and another is this. Oops. There is one that is. This is another like this. So basically, it is something that has very small values or very large values, where it will jump very quickly. It won't go from small to large slowly. It will jump very quickly. So it doesn't go like this. It's not like this. Then you're not able to classify. All rows are having some small, medium, or high. It's really hard to classify. It's row class 1 or class 2. But here your sample gets classified either as low or high. So when that happens in the output layer as the last processing, which is the application of that function, activation function, on the result of all of this, you end up getting class 1 or class 2, or however it is required. So that's how it is classifying in the end. So this is known as the feed-forward process. Now the question is about how do we learn the weights and how this complete sum of products equation will look like for, say, if you had one hidden layer. As you see, this is just repeating what was told in previous slide, but it's showing in terms of the equations. So you have input x's, you have a hidden layer. As I said, whatever is going to the hidden layer is a sum of products. The theta here is the weight matrix. That's what you wrote here. So a lot of sum of products at each layer are happening. At each neuron in the hidden layer is happening. So this is the sum of products of whatever arrows are going into it. This is the sum of product of what arrows go here, the sum of product of what arrows are going here. And if you notice, every input node is being connected to every other node in the hidden layer. So this is called a fully connected neural network. It is not necessary that you have to draw all lines always. So the way you design how many neurons, how many layers, how many connections, fully connected, partially connected, all this is known as an architecture of a neural network. You can have different kinds of architectures. Whatever suits your problem better, the better it is. So in a fully connected neural network, if your weight is equal to 0, it is equivalent to saying that that edge does not exist, because when you multiply with 0, that does not exist anymore. Because 0 times x1 is 0, it's not adding up. So that is another way. So if it's fully connected, then all your weights are non-zero. So A3 is again a sum of products of whatever arrow is going in. So sum W1 x1 plus sum W2 x2 plus W3 x3. The weights are different here. It's not the same W1. It's another W1 times x1 plus another W1 times x2 plus another W3 times x3 goes into this neuron. Same thing into this neuron. So each one has its own weights. That's why each neuron has its own weight vector. Here theta 10 is different from theta 20. Theta 11 is different to 1, theta 31. So everyone has its own set of weights. So you're doing sum of products, you're passing it into activation function. You get the output for this neuron. And then what you do the same thing. Again, sum of products. So in the final layer, again, you pass the sum of products. But here your inputs are these variables, A1, A2, and A3. And then you pass it into another activation function, you get the final result. Thing to be aware of here is you have only 3 inputs, x1, x2, x3 in this example, but if you notice there is an x0 before. This is known as the bias term. So this is like whatever is not being explained by this. This is like the mean effect, the bias effect, right? It is basically, it's like an intercept in your linear regression. It is just translating your data a little bit. Operation with respect to your data set is happening here. Okay, so in the feed forward step, all of this can be written down in simpler notation. You have, so if you have this input layer, you have a hidden layer, you have output layer. So any sum of product, whatever goes into any neuron is a sum of product, right? Is a sum of product of weights on these rows with respect to the inputs. So that can be written as a matrix times a vector, because if you recap how a matrix multiplication happens with a matrix times vector. Now, this, right? Say you had a matrix, say you had 2 rows and you had a 1 vector. So how do you do matrix multiplication? You multiply this whole row with this whole vector, which means first entry plus second entry multiplied by second entry plus third entry multiplied by third entry. What is this? This is exactly sum of products. You're creating products and then you're adding them up. That operation can literally be written as an operation of a matrix multiplication between a matrix and a vector. So since we said our neural network is doing sum of products, right, in all of these slides and even the one before, this entire sum of product operation can just be very easily encoded when you program it as a matrix times a vector, a weight matrix times your input vector. Now what happens? That theta 1 times x, this multiplication, the result of it, you store it in a variable z. That on that you wanted to apply, we apply the activation function, so you pass that into the activation function. And you can keep doing that for however number of layers you have. So that's another way of writing. That's why he wrote vectorization, right? This, how are you encoding this, using matrix algebra, this whole operation, these equations in terms of coding it. So then now there are other kinds of architectures, like I was mentioning. So this is another architecture where until now the pictures were showing one layer, hidden layer. And obviously you always have an input layer and output layer. Input, you pass the data in, hidden layer, then output. This is an architecture with 2 hidden layers. So you have layer 2 layers. And like I said, a tuning parameter is to choose how many layers, and also another tuning parameter is how many neurons. So like you see, here you have 3 neurons, in this layer you only have 2 neurons. It's up to you. You can put 3 here and you can put 300 here if required, right? Depending on the situation. Okay, so here he's talking about, we are not going to cover this. Here he's talking about multiple output. If you have a multi-class classification problem, if you want to classify any input image as whether it's a pedestrian or the computer needs to automatically say detected a car, detected a motorcycle, detected a truck. Then you have 4 possible outputs. It's not two classes anymore. So that's what he's talking about here. We don't want to go to it right now because we want to do binary class classification first for our project. Binary class classification, we will do a standard activation function. So there is no confusion. That we've covered already, which is your sigmoid function. All you need. It will classify it as 0 or 1, which is class 1 or class 2 in the end. Okay. Yeah, these are things that would not be directly useful for you for practical purposes, but all he's saying is algebra as well. Just like we used matrix algebra to show the sum of products and all those operations, you can use and, or, not, and all these operations to represent the same thing. I want to do that at this point because that's not what we will use practically when we implement this. So that's the architecture of a neural network. You basically have input layers, hidden layers, and output layers. It is interesting, especially in computer vision or image processing problems when you apply it. It's a classification problem, but you have handwritten images of different numbers. People have different handwriting. So this 5 is by one person, this 5 is another handwriting, there's another 5. There are different variations of all numbers. But say a problem was for to build a model, a neural network model that will automatically look at each image and say what number it is. So if looking at this image, it says it is a 6. So all 6s need to be classed as 6s, 5s as 5s. So you don't want to say an 8 is a 9 or a 3 is a 2. You know, that's a wrong classification. So all he's saying is, we've discussed above, like any other data set, you would convert each data set into an input variable, each image into an input vector, you pass it in. But what is happening is the follows. If you plot the result you're obtaining at any hidden layer, it's interesting that you will see some very interesting visual representations. So this looks very interesting. This is not looking like your original numbers. This is what is learning at each hidden layer. It's just showing that. Basically, when people do complicated problems like this, when you plot each hidden layer, you will see different resolution that you're looking at. So here it is a very low resolution. You're looking at so zoomed up, you don't know what is common enough pattern to distinguish one number from here when you're looking at it. But when you see different layers, you will see that whole pattern emerging. Each layer is contributing to some amount of intelligence in differentiating one number from another. To be more clearer on how some numbers will look different in terms of looking at this plot. Nevertheless, all this is input, right? It's like black magic, but in the end, the output, as long as your classes come out correctly, you're fine. Which is what is going to usually happen. You're not really concerned about how the hidden layer looks like. It's just fancy to look at it, unless you have some specific computer vision problem in mind where you're really bothered about how that hidden layer looks like. Okay, now the question is, we understood what the architecture is. The question is, how do we learn the weights? Because that is the unknown variable. In the end, for a neural network to be learned, all you need to learn is the weight matrix across the entire, all layers, all neurons, everything. So the technique that is used is basically, this is an older technique, batch perceptron is way too old. The one we would use is called backpropagation. So the technique we would use is known as backpropagation. It's used to learn the weights, and how that is done is as follows. Let me show you the picture and then talk through it. So say you had a neural network like this, right? Like this, for example. In backpropagation, you start with random weights. An intelligent way of choosing weights. In first iteration, start with random weights. You do all the operation of going through all the math, right? So you basically apply all these equations. In the end, you get some result. And then you know what your error is. Because if you apply random weights, obviously you're misclassifying ones as zeros and zeros as ones, you know. Spam becomes no spam, no spam becomes spam, all that kind of mistakes. A lot of error. At each record, you pass, and then the amount of error you totally got, you backpropagate and you pass that back into your backpropagation routine as second iteration. So it takes that as feedback, and then it tries to correct for the weights. It tries to improve and put up the weights. And the whole aim is to reduce that final error of misclassification. So that cycle keeps happening. You start with random, you predict something bad, you know what the error is, you propagate that back into it. That's why it's called back propagation. Send it as feedback. Then there's some more iterations that try to improve the weights. And as you keep improving the weights, the error keeps reducing, but you keep doing that feedback again and again. So it improves the weights in those weights that are contributing to more error are improved more so that the error can be reduced quicker. Those weights that are not contributing to much error, not much of perturbation is done there. So it's like optimizing it for a while. You do that for many iterations. And then at some point it converges somewhere. And then you have the final weights that give you lesser error. And then you use those weights and then you finally make predictions, whatever it says the input is supposed to be. Each record gets classified as one class or the other. So that's the back propagation idea. And from a math point of view, what is happening? So this is your classification error that you're looking at. From a mathematical point of view, what does it mean to minimize an error? Basically they apply what is known as gradient descent. So if you had there's a technique called gradient descent in general, nothing to do with neural networks, although used in neural networks as well. Function like this. So if you see, this is your minima, right? And this is another minima, local minima. This is the global minima. This is the minima. If this was your error function, you want to figure out what weights give you the least error, right? So you want to find out the weights. So this is the weights. So how do you do that? In general, if you have any function that you want to minimize, be it with weights, whatever, in generic function, say I gave you a function x cubed minus 2x squared plus 7x minus 5. And then I said, for what x is this function the minimum? So you need to figure out, right? So the minimization problem is done by gradient descent, a technique, and maximization is done by gradient ascent. What is this technique? You start somewhere saying that, let's assume this is what I would think my initial minima is. Since you're starting somewhere, it will be a bad choice in general. So say you started here. Now you want to improve upon this. What you do is you compute the gradient at this point. What is gradient in calculus? It's basically the slope. So you're doing the derivative here of this function. So you get the gradient like this here, and then you try to perturb your point a little bit in the direction where the gradient increases the most. These are different directions you can take. Over the function. So the gradient gets increased when you go in this direction, right? Gradient gets decreased. So you keep going like this. You keep going like this. Whenever you have the most steepest gradient in that path, you take your next iterate. So the point goes here. Again, it knows if it moves here, nothing will change much. If you move like this over the function, so it keep on going down like this. It gets stuck here because it's a local minima. If you had a function that is convex, then it will find the global minima. But this is a non-convex function, which means you have multiple minimas. So it gets stuck in some minima. So neural networks is a very complicated function. This whole thing that we are doing, sum of products into activation being passed again and again like a recursion from here to here. It is a very non-convex problem, which is what he's mentioning here. So gradient descent on a neural network yields a local optima. But it is better than having something even like some place that is not a local optima. So at least you have some error, some improvement over where you initially could have been, which could be much worse. And then there are other techniques in optimization theory in general in math where you can try to improve your local optima and come out of it and find a global optima and all that. But those are finer details internally. We can discuss that separately if you wish. So that's how the whole thing goes on. So first you're propagating, and then you get some errors. The errors go back. You're sending feedback, and then that happens, and then your weights get improved. You keep doing that again and again. That is the intuition in general. So here he's talking specifically about what that gradient is for that error term. So he's literally writing down the derivatives basically. Also, if you want to look at how the error function is written down, if you see this slide, kinds of loss functions that you could use. There is one loss. So basically, what is a loss function? Basically, your output of whatever it is needs to be as prediction. So if your output label is possible to 1 when you make a prediction, it needs to be close to 0. So what they're doing, different kinds of loss functions that you can use to measure it. One loss function is called entropy loss. So this is a very vast area, right? the loss entropy. So if you look at that, you will see it will have a similar equation as this. That's what they're minimizing as part of the weight that will improve their entropy situation. Again, whole back propagation pseudocode. You compute weights by propagation, then it is once you have the final output, you are seeing how weight is from your input label y. So you have now your loss function, and which will based on your error detection possible. So that's how you are perturbing your weights. Basically. Okay, so I think that our time for today. Next class, discussing more practical details from a coding perspective on how you choose the number of neurons and any other mathematical questions you have in case, etc. Any questions? Okay, so let's call it a day. Keep working at your project and following up on it. Ongoing assignment, minor assignments on the neural networks in general, which will be like a coding exercise, just using existing functions. So it will be like a little blog article that you can repeat or something like that. All right, thank you. Yep.
Thanks.
Okay.